a negative pressure, it turns out, and then negative pressures in Einstein's theory actually cause things to move apart.
Okay.
That's right.
But in the cosmology model, you're going back to an infinitely tiny particle, string, whatever.
Mm-hmm.
So that's going to be reducing the distance between objects.
That's right.
Okay.
That's right.
That seems counter to what happened, because
Right.
the inflation blew. I don't understand that part.
The way to think about that is that dark energy is pretty weak compared to this room, right? The amount of dark energy in this room is much, much less than, I did this calculation once, and it's something like half an electron mass over the whole size of the Earth is sort of the amount of dark energy we have. Locally, that's really weak, and everything in this room gravitationally dominates that. So the attractive gravity beats that anywhere you can look in the solar system. But if you get to the empty regions of space, and there's enough empty regions of space for the dark energy to actually be the most dominant thing right now. But it's not true locally. So in the early universe, it turns out that everything, everywhere, dark energy was weaker than everything else. So the matter, and we're talking about, a very small universe. You're talking about a universe in which matter and radiation were much stronger than dark energy at the time. Dark energy also has the funny property that it's not conserved in the same sense that regular energy is. The more space you have, the more dark energy you have. We think it's actually and this could turn out to be wrong in 5 years, but we think it's actually just a property of space itself. If you have a cubic meter of space, you have a cubic meter worth of whatever dark energy. The density is always constant. That may not be true. That's one theory of it, but that's the idea, and that's maybe a way to start thinking about it.
All right. Thank you.
You're welcome.
What is the strongest technical approach you know of to go out and find some dark matter and actually measure it? And is dark matter going to have its own periodic table or what?
That's a really good question. I suspect that this is the best approach, is actually colliding things in a laboratory and looking at higher energies than you have right now. People had thought for a few years that neutrinos might be the answer, but there turns out not to be enough of them, and they have to be. It doesn't work out because there's not enough neutrinos in the universe given their size. They're really tiny. They're too small, essentially. But I expect that if there is a dark matter candidate that comes out of this would be something like the periodic table that you'd see. This is the periodic table analog for the fundamental particles in the universe. We've got 3 generations. In each generation you have 2 quarks and 2 leptons. This could have more. There could be what Brian Greene, as somebody brought up, calls supersymmetry, which is another popular theory that could be borne out by the Large Hadron Collider stuff. But essentially, you go to higher energies. You look at the universe in a new way, the way the LHC is doing. You're bound to find some things some things you expect, some things you don't. So I imagine that my gut feeling is that the LHC is probably the best chance of detecting dark matter soon. There's other people that are sort of looking at it by kind of the same way similar approach they use to detect neutrinos. They use big pieces of matter and look for really weak interactions between particles that may be out there of dark matter in their experiments. But that could be hard.
Hello, I've got more of a philosophical question, but with the static universe and everything being just right, and the forces and everything, do you think that could be used as an argument for the intelligent design of the universe and religion? Is it exact enough, in your opinion?
You mean, well, I'm sorry, could you say the part about the static universe again?
I mean, like, with the static universe, it's a very unstable condition for the universe, so the universe had to be created just right for it to happen.
Well, this universe isn't static, right? It's actually expanding.
But if it had been just slightly off, then it would have expanded before the universe could have even formed stars and stuff like that, or would it have crashed right back in just a couple of million years? Right.
There are certainly people who think about that. They talk about the anthropic principle and the weak and strong versions of that. It's actually outside anything you can actually measure or test, right? So it falls outside of the realm of science, but it's certainly an interesting discussion to have. I agree. And you could certainly make that argument. You could probably make a counter-argument to it. And My expertise, I apologize, is not in that area.
Okay.
So-
It's just, I've got friends that would be very interested. They're religious people, and I'd just be interested in how I could talk to them about this. Thank you very much.
Oh, you're welcome.
Yes, when the WMAP curve, all the points fit exactly except the last 2 points, and that worries me. Will the Planck telescope show correct that, or is there possibly something right there? Is there possibly something going on we don't know about?
Which are you talking
Last
about?
2 points.
The right side?
The right side,
Here?
yeah. Always worried me.
You can see the error bars here are quite large, right? This is the 60. I don't remember which conference level this is. In fact, this actually, I'm showing old data here, and this is WMAP kind of loses its sensitivity out here, but some ground-based instruments have actually gotten this curve so that they've discovered the third peak quite nicely, and it dips down very nicely here. So it's actually, this part has actually been fixed, or not fixed, but it's been measured better. These are big error bars, right? So you expect a third of these to be off, right, just according to standard Gaussian statistics.
This is more of a political question.
I'll do my best.
If the if the super collider had been made available, what benefit would you expect to have happened to this work?
The super collider would have, I don't know what the schedule was, but it would have gone to higher energies than the Large Hadron Collider, certainly. This is a little bit outside my field. I don't deal directly with this stuff, but I personally, from a scientific point of view, it would have been fantastic. It would have been really nice to see that kind of thing happen.
I just want to clarify something before I ask my question. I'm studying aerospace engineering. This really isn't my field. When you showed the 3 different possible shapes that the universe might be, like for the spherical one and the curved one, that's just surface area, right? In terms of like for the globe, like you're saying,
right.
The possible shape of the universe is just the surface area of that globe, or is it inside it too?
It's
the volume.
This is a tricky thing.
Right.
It's not the volume. It's the surface of this. That's right.
Right. That's what
right.
I was asking.
Oh, yeah,
So
that's right.
Okay. Well then.
Right.
That being the case, then.
But you have, sorry, just to clarify, it's not like we live on the surface of a two-dimensional thing. It's actually an analog of a dimension further. So if you write down the equation for a surface of a two-sphere, you can add a dimension to it, and that's kind of.
Okay, I think I understand what you're saying, but I just want to clarify that. My question then is, what's in the center of that? If everything's.
That's a good question.
Yeah. I just didn't know if there are any theories out there. I don't know a lot about cosmology.
It may be.
Didn't know if there are any.
That's a really good question, and people have asked that sort of stuff.
Okay.
No one knows. There could be nothing.
Okay.
It could just be that the nature of the universe is such that it's a curved. It's like a curved surface of a sphere, and there's really nothing in the middle. It could be that there's other people have talked about something called M theory, where there's lots of different. There's another dimension that separates another one of these spheres, like you have a sphere inside of a sphere or something like that, and that those can actually move relative to each other and all this kind of stuff. So they're definitely, that's a great question, and that's exactly the kind of question people are asking about these kind of things. Thank you again.